Some examples of using roots of unity to solve some contest math problems. So first one is divisibility of polynomials. The second one is polynomial equation. And then the third one is from AMC 12. It's related to complex number equation with complex numbers. So some basic theory about roots of unity. So we will do this in the case when x is like fifth root of unity, but you can generalize this to any number very easily. So if x to the power 5 is 1, what's x? So that's the question. So the real root is x is equal to 1, so that's the first obvious one. But the thing here is that since the degree of x5 is 5, there has to be 5 roots. So there are 4 more roots that are not real. So there are like 4 more complex roots. So how do we solve this in general? So you can write the equation as x5 minus 1 is equal to 0 and factorize this x to the power 5 minus 1 as follows. So it's a factor x minus 1 and the rest x4, x3, x squared, x plus 1, the sum. So the first parenthesis has the root 1 and the second parenthesis has is a fourth degree polynomial. That's why it has 4 roots. But we don't know what are these roots. But it turns out these are complex numbers. And you can do some operations for some cases. It's easy to find these numbers. For some, it's not very obvious. But it turns out, so when in the case when x is equal to n, xn is equal to 1, these roots have some very interesting property. They are all complex numbers. So if you plot them in the complex plane, so this is a complex plane, and if they are all located on the unit circle, so this is real axis and imaginary axis. So the 5 roots of this equation, and they are all located on the top of this unit circle, and they are uniformly distributed along the unit circle. So and the first one is obviously here, which is x is equal to 1, and the rest are equally distributed along the circle. So if you have like x to the power 6 is equal to 1, then you would divide this into 6 equal parts and then place those roots. And then using the angles, you can just divide 360 by 5, and using the angles you can find exact values of these numbers. So we are not interested in the exact values of the numbers. So it's obvious, but we are not interested in that. But there are some properties that we are going to use in the upcoming problems. So fifth power of any of these roots is equal to 5. 1 is equal to 1 because they are roots of unity, and then fifth root of unity because from the given. So we are initially solving this equation, right? And then the second property is all these 5 roots have some relation. So the first one is 1, and the second one is omega. The third one is going to be just like omega square, and then omega cube, and omega to the power 4. So basically, we have this very interesting property of the roots of unity. So where we are, so we have these two properties, and so this idea can be generalized to any number n. It doesn't have to be 5, but since we are going to use fifth root of unity in the next couple problems, this I'm presenting as an example fifth roots of unity. So let's see some problems now. So the first problem is the following. We want to prove that this polynomial is divisible by this one. So this is 44th degree and this is 4th degree. So we are going to use a very simple property of polynomials. So let me do some kind of small analogy. Is 24 divisible by 6? So you can divide straightforward, like directly 24 by 6, but there is another way. So just like this is for just illustration, you can factorize 6, and if every factor is dividing 24. So 24 is divisible by 3, 24 is divisible by 2. Then 24 is divisible by 6 as well. So in the case of polynomials, if every root of polynomial is also a root of another polynomial, so every root of q is a root of p as well, then it means p is divisible by q. So what we are going to do is we are going to prove that every root of this green polynomial is also a root of this 44th degree. So what are the roots of this 4th degree polynomial? So it's a part of, from the previous slide, it's a part of factorization of x5 minus 1. So the roots are fifth roots of unity, the omega 1, omega 2, omega 3, and omega 4, where the fifth power of the omega is 1. So these are the roots of this 4th degree polynomial. So if I can prove that these 4 numbers also make this expression 0, or also roots of this, then 44th degree polynomial will be divisible by this green one. So you can just set x is equal to omega I in general case and plug it. And then I'm going to rewrite it as follows. Because these parts, the omega to the power of 40, 30, 20, 10, they are all equal to 1 because it's a multiple of 5. Omega 5 is 1. And then since if you do the multiple, that gets 1. So this expression simplifies to the following, to remove the ones. And since this equation is same as this one, it's as if we are plugging omega e to the equation. That's equal to 0. So that means if I plug a root of this x to the power 4 polynomial to this one is also 0. So all 4 roots, all 4 roots are also roots of this polynomial. Then this polynomial is divisible by this green polynomial. So that kind of concludes the proof. Second problem. Second problem is from 1976. So we want to prove we have this polynomial equation, a relation between 4 polynomials. And we want to prove that x minus 1 is a factor of px. So let's start with the idea that we are going to prove. What does it mean that x minus 1 is a factor of px? It means that 1, so if you solve this equation, so 1 makes this 0. It means that 1 is a root of px. So basically, we want to prove that p1 is equal to 0. So we want to prove that p1 is equal to 0, or in other words, you can try to find the value of p1. So if it turns out to be 0, then you are done with the problem, right? So we have px5 in the expression. So we want to make, I want to make this px5 equal to p1. So there are 4 different numbers that I can plug. There are 5 different numbers actually. I can plug into the equation and then get p1. So I'm going to use these 4. So I'll skip x is equal to 1. I'll use the rest 4. So what happens if I plug fifth roots of unity into the equation? Like this, omega I, 1, 2, 3, 4. I is from 1 to 4. And this part is going to be 0 because it is, these omegas are the fifth roots of unity, and it makes this part equal to 0. And fifth degree of omega I is also 1. So this expression simplifies to something like this. P1, Q1, R1, and we have 0 on this side. So what we can do, let me rewrite for each I. So we have 4 equations. So omega I. So it's like, as you can see, omega 2 is basically omega squared. So instead of writing omega 2, I will write omega square, omega cube, omega 4. In that way, I'll have only one unknown. So that's the idea. So these four equations have P1 in it, but we have Q1 and R1 that we don't know. So I want to get rid of those numbers. So in order to get rid of those numbers, I can multiply each of them by negative omega, negative omega squared, negative omega cubed, negative omega to the power 4. So I have like 4 more equations with multiply. But what we have now is if I sum all these equations, you can see omega squared, this one, and omega squared, they get cancelled out. Omega cube cancelled out with this omega 8, because omega 8 and omega cube, they are equal, because omega 5 is 1. So q's get cancelled, r's get cancelled, we are left with p1s only. And we have 4 p1s here, and then this part from this equation, it's just 1 p1. So if you add the entire 8 equations together, we get 5 p1 is equal to 0, and basically that means that p1 is 0. So when we know that p1 is equal to 0, x minus 1 is a factor of px, and that's kind of root of the polynomial. So that concludes the proof. And the last one, problem number 3. So this is from AMC 12, 2002. Find the number of, so we want to find number of solutions to this equation. So to make it a little bit easy, let me write it as a complex number. So a plus ib is z, and then a minus ib is going to be conjugate of that number. So we have these two numbers. Now my equation becomes z to the power 2002 times z conjugate. So what happens if I take the modulus absolute value of the both of the numbers? So we have this equation, and then since this is I'm going to use some simple properties of complex numbers, so I can take out the power outside these modules and then get rid of this conjugate, because conjugate and then the complex number itself, they have same modules. So I can rewrite the equation as follows. So the absolute value of the z conjugate is equal to modulus, so modulus of z, and then I can take out the, so here the modulus z is a real number, so the length of the complex number. So if I rewrite it like this, I have the following equation. So from here I have two options. Either the z is 0, that makes the modulus of z is 0, that makes a and b equal to 0, so that's one solution, or z is equal to 1 from here. So this one has, as you can see, if you imagine this is x, we have 2001 solutions, but if you restrict these solutions to real numbers, there is only one real number solution. Z can be equal to 1 only, because the modulus z is a real number. So z is 1. So in that case, I'll take the original equation, this one, and multiply both sides by z. So when I multiply both sides by z, I get z to the power 2003, and this part, z conjugate times z, it gives me the modulus. So z to the power 2003 is equal to 1. So that's just modules. Now we have an equation, z to the power 2003 is equal to 1. So we know how many roots this equation has. This equation has 2003 roots, and these are 2003 roots of unity of order 2003. So summarizing from a and b total, we have one root, a is equal to b is equal to 0. 1 here, and 2003 in the second case. So total we have 2004 pairs of a and b that can satisfy this equation.